let's just find his z-score. So the z-score for MJ is 78 minus 70 over standard deviation 3.5. Hit me.
Was that 2.285?
All right, 2.3? You like 2.3? Let's say 2.3.
2.3, 2.285.
Okay. Actually, no, I don't want to set a bad example. All right, 2.29. Okay. Okay. So what is the probability that a randomly selected American male will be shorter than Michael Jordan? How do we solve this question? Yeah. First we use the z-table. Height is something that we could reasonably expect to fall into a normal distribution. One, because there's such a huge population. So,
0.9890.
okay, so the z-score is 0.9890, or not the z-table, the area under the curve for that z-score. All right, so 98.9% of people are going to be shorter than Michael Jordan.
So you say 98.9%
Right here.
people?
Yep. Yes. Yes.
And that's your Z.
So if his z-score was 2.29, the area under the curve associated with the z-score of 2.29 is 98.9%. So where does Michael Jordan fit on this normal distribution? Is he right here? Is he right here? Is he right here? Yeah, right about here. This is MJ. All right, and we know that percentage of people taller than him, what's that, 1.1%? 1.1% of people are taller than him. So if he goes to parties, he has a 1.1% chance of being shorter than someone in the room. Now that's not really an accurate question because it's not a fair sample, it's a biased sample. Because Michael Jordan probably hangs out with basketball players, right? So if he goes to parties, there's a chance that people are going to be on the average taller. So if he had a big list of every single party he could go to in the entire country, and he cranked some lottery wheel, and like pulled out, all right, I'm going to go to this particular party, then that would be more reflective of a, almost 99% chance of him being taller than anyone in the room. Okay. Suppose further Isaiah Thomas, short guy, has a height of 69 inches. What is the z-score for his height? The z-score 69 minus 70 over 3.5 equals negative. Yeah, negative is right.
0.285.
0.285. Okay. All right. So where does Isaiah Thomas fit on this bell curve?
On the beginning.
What's that?
The beginning, right?
No, not quite. This is a tough one. So it was not a completely fair question for me to ask because it's fairly close. What I'll point out to you is it's fairly close to 0. If it were 0, it would be right in the middle. So it is just a little bit to the left of 0. Isaiah Thomas. Okay, now, the thing about the z-table is it is symmetrical. Probability below the median is the exact same probability above the median. This curve breaks exactly the same way, just like it did with the heads and tails experiment. The chances of getting 5 heads is the exact same chance of getting 15 heads. So we can use our z-table. And I skipped over this one, I guess, but there's a larger z-table, so you don't have to use a magnifying glass, on the back of page 11. Right here. So let's look up the z-score for 0.28. Let's call it 0.29. Alright, so on the left-hand side we go to 0.2, and then we go across to 0.29, and we get 0.6141. Okay, so that's the area under the curve for positive 0.29. If his z-score were positive 0.29, which is not, then 61%, it would be like this, let me get a different color. I can erase. Alright, then 61% would be in here, 61%. Okay, if it were positive. What we can take from that is what's the difference between 61 and 50? 11%. So we can just use the mere opposite of that and say there's 11% difference between Isaiah Thomas and the mean. So we're going to erase this funny color. And we're going to say that 39% of people are shorter than Isaiah Thomas.
So you take the 11, subtract the 60. The 50.
You like that, John?
Just one more time.
39% of people
Yeah.
are shorter, males are shorter than Isaiah Thomas. The next guy who walks by that door, there's a 39% chance he's going to be shorter than Isaiah Thomas. Okay, so last question I think on this slide, don't get excited. Last question on this slide is what are the chances that an American male, i.e. the next guy who walks by, will have a height in between Isaiah Thomas and Michael Jordan?
So is it 78 minus 61?
Well, what's your name, Richard?
Richard.
Derek. Alright, so 39% of people are shorter than Isaiah Thomas. 1.1% of people are taller than Michael Jordan.
Also, you don't add it.
Where does that leave here? So, 39% of people are shorter than Isaiah Thomas. 1.1% of people are taller than Michael Jordan. What percentage of the people are in between?
Which is the 61.
60? Yeah, 50, 59.
9 point something.
No, I did 11, because you had the difference between the 39 and the 50 was 11, and then you got the 50, so it's 61. That's what I did.
59.9.
I see where you're going. It is a matter of adding these up, but the thing that you need to add up in this particular question is this and this. You need to subtract both those from 100 and you get the answer.
So you added
59.9.
you added the 39 and the 1.1,
Subtract that from it.
so that's 40.1, and then subtracted that from 100. Okay.
So just look at it detail. Like 39% of people are shorter,
Yeah,
1.1% of people are taller. So what does that mean?
everything in between.
Everything in between?
Yeah,
Yeah, whatever it is.
okay.
All right. How are we doing with this? We like it? Okay, good. Let's try that next example, bottom of 15. Suppose the driving distance to work for residents of a certain community has a mean of 23 miles and a standard deviation of 3.6. What is the probability an individual drives between 19 and 26 miles to get to work? Assume that the distribution is normal. Assuming the distribution is normal is key here. Because once we do, and we have the mean and the standard deviation, we can calculate an answer to a question exactly like this. So for this one, we're going to need 2 z-scores. We're going to need a z-score for 19 miles. We're going to need a z-score for 26 miles. And we're going to do the same type of thing. Let's add up the space in between type deal. All right, so you process that for a minute. Let me make some space here. All right, so let's get the z-score for 19 first of all. Z-score for 19 is going to be 19 minus what?
23,
Yes, divided by what?
3.6.
3.6, yes, equals
12 plus
12? That sounds a bit high. I think it's,
Oh, negative.
It's negative.
That's,
Nope, 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 negative 4.
it's negative 1.11.
negative 1.11, I like that.
Yes.
All right, so how about 26? 26 minus 23 over 3.6 equals, nice, 0.8333. Okay, so we've got our normal distribution. Alright, we have a mean of 23. We have a standard deviation of 3.6, and we can assume normality. So we've got a z-score of negative 1.11. Alright, this is the center here. Call that the center. And we've got a z-score of 0.833. So this is z. Z's. Okay, so what do I do next? Actually, let's not look at the chart next. Let's just think about, I did something here where I added up this and the difference left in the middle. What am I going to do over here that's similar to that? Difference of some sort. So this negative 1.11, alright, and this 0.8333. What question am I trying to answer? What does the question ask us?
What is the problem?
Yeah, so this is 19 miles. This is the z-score for 19 miles. This is the z-score for 26 miles. And I want the probability of being in between these two.
Right.
So do you think I want to add this to this?
No,
No. What do I want to add?
those two.
Yeah, I want to add, I want this stuff in the middle.
Middle.
Okay, so that's what I want. So I'm going to have to do some backwards type thinking when I look up the z-score for negative 1.11 and 0.83. But let's go ahead and do that. Let's look up 0.83 first. Okay, so the area under the curve associated with this is 0.7967. So what does that mean?
79% are less than
Yes.
26 miles.
Yeah, so I think the easiest way to solve this one is what percentage are more?
So 79 minus, 100 minus 79.
21%?
All right.
I think that's the best way to look at this one.
20.33.
20.33%, okay. All right, now let's look up negative 1.11. And we're gonna have to do
0.86.
double duty here. So that's for 0.11, right?
And then
One more.
Are you gonna?
All right, so you look up 1.1 and you get 0.865, right? So that would mean there's like roughly 14.
13.35.
Yeah, so 13.35 if it were positive would be higher. But since it's negative, 13.35 are lower. Does that make sense? So this is 13.35%.
How did you get that?
All right, question?
Yeah, where's that coming from?
All right, so, what's your name?
Barbara.
Barbara. So Barbara, what did you start? You looked up 1.1.
Negative 1.11 is 0.8665.
Okay.
And what I did 100 minus 86.65, which gets me to 13.11.
Okay.
Okay. So the question is, what's the probability that any one particular person will have a commute between 19 and 26 miles? Sounds reasonable. Yeah, you just subtracted, the difference, whatever was left out of 100. Yeah, 66 point what?
32.
Okay, I like it. No argument here. This area in between, 66.32. How do we like it? Okay. This is the key problem for tonight that we'll build on. The binomial stuff is warm up. Go ahead.
That's a really good question. Why wouldn't we add
6.65%.
outliers, the standard deviation negative 1.1 plus 0.833, and then subtract it by 100? Why wouldn't you do that?
Why wouldn't we, you mean like add this together and get like negative 0.3?
When we did that, when we added outliers, we subtracted it by 100, right? Why
Oh,
wouldn't
okay.
we do that here?
Yeah, so what we were, yeah, we did the same thing. So we said 39% is on this side, and we said 1% is on this side. So we had 100 minus 39 minus 1.1 equals whatever we got. And we did the same thing over here. 13% is on this side, 20% is on this side, 100 minus 13.35 minus 20.33 equals 66.32.
Yeah, but we did a little differently. So you're saying you have to have the z-score for 0.833 before you can actually do the math?
Yeah, that was my first question. Were you saying we just add these together
Yeah, I
and
thought you
get like negative 0.3?
That's what I thought initially the first video. You're saying you need the actual z-score and then between the two.
Yeah, because if you look, like, the area changes here. So negative 0.11 is very specific about the area to the left of it. If we were to put these together, then we would be comparing a different sliver that would be way up here. If that makes sense. So just, good, good.
Can you go over how you got the 13.35%?
Yes. Yes. Okay, Barbara.
Yes,
Alright, so the question is, how did you get the 13.35%?
so I added the two ends, 20.33 plus 13.
No, how did you get the 13.35?
Oh, so I did the.
So
the
first you get,
table?
yeah, first you get the z-score of negative 1.11.
Right.
Okay, excellent. And then what'd you do, Barbara?
I got the table, whatever I got for the table was 0.8665. So I made that into a percentage. I did 100 minus 86.65, and that came out to 13.35.
So she looked at, the z-table will tell you if it were
That was a
positive
number.
1.1, then that would mean, what is it, 86? 86.65?
0.65, yeah.
If it were positive, then 86.65% of the data would be lower than that, which would leave this amount higher. And since it's negative, it's just the opposite. And this is the 13.35. Okay, all right, you bet. Okay. All right, so, good. Let's see what else we have. I'm gonna get through this. I tell you, no matter what happens, we're not getting out before 9:30, so nobody get excited, right?
Okay.
So, just know that. All right, so, zero probability. All right, because I skipped around a little bit because I wanted to get some momentum going. Let's see. Normal distribution, we've got z-scores on page 12, we're looking good. We did an example of the normal distribution. We did the male height example, we did another example. All right, now we're going to talk about, on the top of page 16, we're going to talk about frequency distributions, which you already know about. Then we're going to talk about measures of central tendency and measures of dispersion, which is all going to be easy stuff. All right. So take a look at the frequency distribution shapes on the bottom of page 16. Let's just look at the ones on the left. The top one is symmetrical, the middle one is positively skewed, and the bottom one is negatively skewed. All right, so almost all of the time in this class, with the exception of the next 10 minutes or so, all of the distributions we're going to be concerned with are symmetrical. Because if they're symmetrical, we can use the z-score to make important assumptions about them. Positively skewed, though, is something we want to be aware of, and we want to know how to interpret that. So positively skewed means that the numbers on the higher end have a greater probability, or they're more extreme. So in that tail or coin flip example, there'd be a higher percentage chance that you would get 19 or 20%, or 20 heads, than there would be that you would get the lower ones. Just means that the bigger numbers are more representative, or not more representative, the bigger numbers have a larger effect and they pull the average up. The negatively skewed is just the opposite. Let's take a look at a couple examples to put that in context. Again, I'm jumping around. Okay, all right, yeah, before I go to those couple examples, I want to look at the bottom of page 17, and I want to talk about the measures of central tendency. Mean, median, and mode. What is the mean? What is the median?
Middle.
Middle number, if you line all the numbers up, the one in the middle is the median. And what's the mode? Yeah, the most frequent one. Now, mean and median are sometimes used as the measure of central tendency because the mean can be affected by significant outliers. If you have one really, really rich person in your neighborhood, that person is going to pull the mean salary up in a way that's not going to be representative of what the neighborhood is. The median number in a case like that may be more representative. Alright, so now we're ready to get to my two examples which show us symmetrical positive and negative skewed. Let's go to page 21. Alright, suppose you have some income statistics for a town in New Jersey. You collect a bunch of data, you see that data, the mean income is 60,000 for each family, the median income is 60,000, and the mode is 60,000. That distribution is even, it's symmetrical, and it is a normal distribution. Mean, median, and mode are all the same. Now, let's take a look at an example on the next page, top 22. Suppose we have a different town where the mean income is 80K, median income is 60K, and the mode income is 60K. What's going on there?
Somebody with a higher income.
Yeah, there could be one person with a really high income who is pulling the mean up. There could also be a group of people with higher incomes who are affecting the mean. Now, the key here is it's not that there are more people who are in the upper income levels, it's just that the people who are in the upper income levels have more of an effect on the distribution. So it could be just one really rich person screwing everything up. Okay, how about the bottom of page 22, the opposite example. The mean is 45K, median is 60K, mode is also 60K.
There's one really poor person.
There could be one really poor person, yes. There could be one, depending on how
That's so nice.
it might be more likely that there's a group of really poor people, because if we turn back to bottom of page 21, there is one really poor person, right? There's at least one really poor person in that distribution too. And it's just that there's a group of them that are really, really poor.
So, on the top one, on page 22, you have one really rich person pull it up, or you can't really have one?
Well, you could, because that person could be rich to infinity, right? But in terms of the one poor person, all you can be is 0.
Like your own one? Is that-
Yeah, yes, you could owe. Yeah, you could owe. That's a possibility. Alright, I guess we could look at it that way. So there might, in that bottom one, and again, the key here is it's wrong to say that there are more people who are poor, or there are more people who are making less than 60,000, because there are 50% of the people are making less than 60,000, 50% of the people are making more than 60,000. It's just the people who are making less than 60,000, they're more poor relative to the people who are rich. Make sense? Yes?
I understand what you're saying, but like you're talking people, and this just says like family, income.
Okay.
So really you're just looking at dollar units per residence.
You're right, I should have said family.
As far as the family or.
Yeah, I should have said family. You're absolutely right. Instead of saying people, I should have said family. So it could be one really rich family pulling the income up,
Right, yeah.
or a group of really poor families pulling the income down. Okay, everyone have that? Yes, sir. All right. All right, so standard deviation. Let's take a look at the top of page 20. We already talked a little bit about standard deviation. We said that really skinny bell curve has a small distribution, and the fatter bell curve has a wider distribution. And that can be represented with standard deviation. Definition for you, top of page 20. Standard deviation is approximately the average distance between the individual values in the data set and the data center. So the data center being the mean, what's the average distance from the mean? Here it's wide, here it's small. Or here it's large, here it's small. Is the best way to say that. So if you look at the bottom of page 20, you can see that little s is what we use when we're trying to calculate a sample standard deviation. And the sigma, the O with the little hat, is what we use when we're calculating the population standard deviation. And the population standard deviation is what we've been working with in our examples so far, and what we will often work with in class. It just means that if we have every member of the population, and we calculate the average distance of each member from the center, then we have the population standard deviation. If we just have a sample, all right, say you all are a sample of Mercy College students, and I were to ask you your grade point averages, all right, we'd have a sample mean for grade point average, and we would have a sample standard deviation of the 19 of you. The only difference in the calculation, you can see the sample mean, you see that it is divided by n minus 1 in that calculation, versus the population mean is divided by n, in capital N for every member of the population, small n for the sample size. So dividing by that n minus 1 means there's a smaller number than denominator, so it's a slightly bigger number. So for example, if I'm going to divide 9 divided by 3 equals 3, but 9 divided by 2 equals, what does it equal, 3.5 or something? 4? Oh, bigger, sorry, 4.5. Okay, so dividing by the smaller number gives us a slightly bigger number. The reason for that is if we just have a sample, we want to make the number a little bit bigger to account for possible error. When we're making statements like we're 99% confidence that the true mean is between this and this, we want a slightly bigger number if we only have a sample.
We're still subtracting x bar equals mean, right?
Yes, x bar is the sample mean,
Sample mean, but the mu is also equal to
is the
mean?
population mean.
Population mean, sample mean.
Yes, thank you. Good catch, as I'm trying to rush through this. The x bar is the sample mean, and the u is the population mean. Actually, I think we have that. Let's go back to top of page 18. Mean, as we all know, is the average of a set of data. And you can see x bar, if we just have a sample. Again, if you all are a sample of Mercy College students, I'm going to ask for your grade point, I'm going to average it all up, I'm going to divide by the total number, and then I'm going to have a sample mean, and that's x with a bar on the top of it. If I were to ask every single Mercy College student, then I were to add up all of their grade averages, divide by the total number, then I would have the population mean, which is notated with that u, sometimes called mu. Okay, so we've got median, we've got mode, we've got measures of this, and we're in the middle of a discussion about standard deviation, and we just did a quick side note for mean. Okay, so I have a little calculation at the top of page 21, which we could do really quickly, but I'm just gonna leave that one alone. And yeah, I'm gonna tell you that the takeaway is that the sample standard deviation is gonna be a little bit bigger. We're going to divide by a smaller number so that we get a little bit more of a cushion. So you can see that example on the top of page 21. The population mean comes out to 1.7. The sample mean comes out to 2.08.
sample always has to be 20 or greater?
We'll talk about that later, but if your sample is 30 or greater, then you can make assumptions about normality. It doesn't have to be, but you can say, if I have a sample size of at least 30,
Okay,
then I can start using this type of stuff
okay,
and make these types of assumptions. My sample size is,
30 or greater.
yes, if it's 30 or greater, I can get into this good stuff. If it's less than 30, I can say, well, I mean, you know, I know that the normal distribution says this, but I have a small sample size, so I may not be able to rely on that.
Okay, so even when you're doing the n minus 1, so that your final answer is larger, that doesn't balance out, whether you do to the 20 or the 30.
You're right, it is, it does, it
It
balances out.
does. It
Because
does
what
balance
happens
out.
is,
Okay,
we don't use the z table, we use
Right.
a t table,
okay.
which instead of looking like this, looks more like this. Wait a minute, now. Which just looks flatter. Instead of looking like this, it looks more like this. We have to account for the possibility of outliers,
Okay,
and we have to use a larger standard deviation. So if we were to do a problem like this number would be larger,
right. Mhm.
right? And we would come up with numbers which would just give us more of a cushion. When we say, all right, we're, you know, this, we'd have to have a larger, what we'll call confidence interval.
Okay, just because logically you know that if you've got too small a sample, it's not really gonna be reflective of a larger population.
It could be, the thing we account for is the possibility of an error. The possibility that we've got unlucky with the sample we chose.
Okay, okay.
So we use a different distribution and we use a larger sample size. Great question,
Thank you.
great question. Okay, so let's reflect on what we did today. We learned combinations. I will tell you, because I feel bad that we just got so bogged down with that combination and binomial formula, that there is, I think, one combination question on the quiz.
How many questions are there this week?
5. It's one combination, so know that combination formula.
When do you post the quiz?
It's already
Post-
It
posted already.
Take it right.
And you get 1 hour, right?
Yes, yes.
Please leave a comment.
Yeah, I think there's one combination question. There's also one binomial distribution question. So it'll be a question such as, you know, what's the chance of success? How many different times, how many different, total number are there in this experiment, which would be our n? And what's the probability of getting exactly 4 successes out of 10 times?
Are they multiple choice or they're filling?
No, short answer.
And if you get it wrong the first time, that's it, you can't like continue trying.
Right. You
So
just
it's
give,
just
one
one
chance.
answer.
This is like kind of
Not like that.
No, when you're doing it though, you put in an answer and then you go to the next question, you realize you made a mistake, you can't go back?
Go ahead.
Okay, once you submit it.
Once you hit submit,
then
you
you're-
can't go back.
Then you're out of luck.
Yes.
Okay.
All right. Then the normal probability distribution, we became familiar with that. We learned how to calculate z-scores. And I'm sure there's at least one problem like this. So calculate the z-score, calculate the area under the curve, calculate the z-score, area under the curve. There'll be at least one problem like that. And there will also be, I think, one problem with that income. Like the mean is this much, the median is this much. What does that mean? You might say something like, well, maybe Donald Trump lives there, or maybe this is like a town where everyone is unemployed, except for the people who, are in this factor, or who do this or that. Alright, so I'm excited to have you all in class. Thank you so much for your attention.
Thank
Look forward to seeing you next week. Good, good. I'm glad you're taking it. I realize this is like, right, maybe next time I shouldn't spend so much time on the back of the
So the prereq for this
We just in terms
So you know how this came out to 796 cents? When I started this? Okay, so I got waivers, so I'm 3 times, so it's not that bad, yeah. I'm only trying to figure out where to Yeah, that's all. Yeah, first time I'm taking graduate course this year, because I've had him on humanity, I had him in humanity and God rights. I hate God rights. Too far for me. And I started to look at options and that's my dream. Because I'm right there, right around here. I'm like, how did I forget? But with work, I was going back and forth, so it was much. So it's not been. Oh, the whole formula. I have, after this class, I have that's the best way to do it, because I did 500 and this class I already took the class so me behind, now it's like, when I went on my pre-audit, I don't remember taking that class. So I registered and had it drop in, but it was alright. I took some time off, so it took me a little bit. So, it was nice meeting you ladies. Yes.
So you are already booked for the first time? I got mine right now.
We already have
This is gonna be the hard
Alright, so let's see, for number one, following to the so these are hours worked. The average so
I'm undergrad too. I took some undergrad twice. First time I got a D. And I did it again. It was impressive.
Yeah, so I didn't quite understand, that's all I was gonna
They sell out easy, those two.
Never will, no worries.
Yeah.
Okay, okay, so you'll pay, and I can send it to you.
So that's good. Oh, you haven't been there, right? To see your office. When did you choose to go?
so you'll
I
have.
wanted to text her, and I haven't
And
sent
you
it. I
actually
want to
need
know
to
she's
read
going
Excel
to.
worksheet for that provided.
But I like Beatrice. It's not tough.
Look at it tomorrow.
While I was in Brooklyn with her, she was no problem.
It's still in history.
And then these people,
How do you sort the blackboard? I never use it.
oh, let's do it.
I'll probably do a whole.
So,
Like I was telling
first of all,
Gail, it actually spells out.
Yeah, I know.
so it's the same thing.
Oh, is it there?
You're gonna go,
The whole book, yeah, 1 through 7 is like half the book. Yeah, I only have half of it on me right now, so it's like for like.
Yeah, that's what helps you guys, we're doing that good stuff.
Yeah, for next week it's just that. So by tomorrow, I'll do 1 through 7 by tomorrow.
I might be.
In the morning? Because I'm 1 through 7, but someone else is doing it, but 1 through 7 definitely by
you know,
tomorrow.
I don't know.
Morning.
Okay, because then I'll go into the college.
Oh, that's it?
I have to do it at home, I have to play with it.
I should
I can't.
see all the